We'll resume this poster session by the third and last poster winner, Robert Gowers from Humboldt University in Berlin. And he will be talking about spatial structure filters, how it filters the fluctuation-driven dynamic firing rate response. Thank you very much.
Okay, yeah, thank you for giving me the opportunity to give this presentation, and thank you for the ICMNS organizers. I should really stress that this research was done previously in my PhD, and I kind of continue this forward. So I'll be talking about how the spatial structure filters the fluctuation-driven dynamic firing rate response. So to give an overview of what I'm going to show is that I'm going to look at simple neuronal morphologies, such as those three shown below. We just have two long dendrites, a dendrite and an axon, and a dendrite and a soma. And we're going to calculate the dynamic firing rate response. We're going to do this in the fluctuation-driven regime, where a lot of neurons find themselves a lot of the time, where firing happens rarely and irregularly. And what we see is that spatial models allow for different kinds of modulation and different kind of responses to what we normally would see in point neuron models. And the main takeaway is that impedance loads, such as large soma, or spatial separation between point of modulation input and trigger position for action potential, effectively filter the dynamic response. So as a background, it's been measured and calculated that neuronal populations as a whole can encode information in their population average firing rate and at different frequencies to the steady state average firing rate and the reciprocal of their membrane time constant. So various firing properties, aside from this, have been found to be altered by the distance from the soma to the actual potential initiation site and all the other morphological properties. So as I said before, previous research has focused on point neuron models. So a reasonable question to ask is how the spatial structure, such as dendrites, axon, and soma, affect this dynamic response. So previously, we've used something called the upcrossing approach to approximate the steady state firing rate. This is just an example. And what we found that was the voltage mean and the voltage variance for spatial models gave different firing rates to point neuron models. So we thought if it's different in the steady state case, we'll carry it forward to the dynamic response and see what different effects we get. So this is just a simple example showing that for different axonal sizes, you have a different number of dendrites that maximize the firing rate. We don't need to worry about too much from this. This is just showing what's been done before. So for the dynamic response, if you apply a small amplitude input at a given frequency, then the average firing rate will oscillate at the same frequency, approximately. And in this population response, the firing rate will oscillate about the steady state average firing rate, and it will have an amplitude of oscillations about this. And there'll also be a phase between the modulation input, which I show here in orange, and the firing rate output, which I show in blue. And so the two things we want to take away is the amplitude and the phase. And in particular, in the amplitude, we can, when we say that neuronal populations can encode information in their firing rate, we imply that the amplitude of firing rate oscillations is in some way detectable. So this implies there's a bandwidth to the response, and we're going to just use a simple measure of half the low frequency limit. We're mostly just going to just look at the amplitude though. And then the phase zeros kind of give the frequency at which, if we had two populations that were identical, then at the frequencies of these phase zeros, that if one fed if the output of one was the modulated input to the other, then the input and output would be in synchrony, and this would be the frequency which they're synchronized. So that's the motivation for that. As I said, we're looking at the fluctuation-driven regime, and this means that firing happens rarely and irregularly. And because of this, the voltage voltage trace often forgets the last time it spikes effectively. So we can see that if we don't reset the voltage, so we're kind of comparing with the leaking cigarette and fire model here, if we don't reset the voltage, the two traces between non-reset and reset voltage eventually converge in between firing events. And so we can just, as an approximation, use a calculation of the number of times it crosses threshold. And this greatly simplifies the analysis in this case. And we just require the voltage mean and variance and the voltage time derivative mean and variance. And this has been used before in point neuron models. The method itself of calculating level crossings is a very old technique, but it's not, this is, a new point is applying to spatial models with spatially distributed synaptic drive. So in our framework, we have, as I alluded to, a spatially distributed drive S, and this is, as opposed to a previous talk by James McLaren, the drive is now spatially uncorrelated so the drive is uncorrelated in space, but is temporally filtered. So it's like a conductance based synaptic drive. And we're going to have a specific location where the modulation comes in, XC. So this is formed like a local current modulation. And it's like often what they do experimentally where they apply time varying input at the Soma, for example. But here we're just going to say it comes at position XC. And there's going to be another location XTH, and this is the trigger position. So this represents the point at which an action potential is initiated. And when the voltage here exceeds threshold, the voltage in the entire structure is reset. And in our framework, it's spatially continuous and just obeys linear cable equations. So it's linear model with modulated input driven by temporally filtered noise, which we also take the Gaussian limit, assuming kind of background synaptic bombardment. Okay. So we keep the steady state properties constant. So we want to separate out the dynamic effects from what we found in the steady state. So we're going to keep the voltage variance and mean and the threshold constant when we vary morphological parameters in each of these cases. And as an example, I've shown the point neuron example. So we're plotting the amplitude relative to the amplitude of firing rate oscillations relative to the low frequency limit, and also the phase that I showed earlier. So the theoretical calculation is in the solid lines. In each case, I'm showing the threshold and reset like LIF model with the triangles. So the point neuron model, we don't actually have any phase zeros for this current modulation. There's only one place to put it because it's an isopotential. And the amplitude of oscillations is just like a sigmoidal kind of step down. Okay. So the first model I consider is two radiating dendrites. These kind of radiate from a nominal Soma. We place the trigger position at 0, where these two dendrites meet. And we have the point of modulation input XC. And what we see is that when we increase this distance between the two, the amplitude of oscillations decreases across the frequency spectrum. So when you have a larger distance, your bandwidth will decrease. Oops, sorry. And we get two phase zeros in general, apart from the limiting case where the distance is 0, when we have 1, and also when the separation exceeds a certain value where we have 0, no phase zeros. And this is because as we increase the spatial separation, we incur more filtering of the modulation when it goes from the point of input to the point of trigger position. And the lower phase 0 will increase in frequency, and the upper phase 0 decreases in frequency until they converge and annihilate. We also find that if you make the synapses slower, then you decrease the frequency of the first phase 0. So faster synapses, alternatively, faster synapses require a smaller separation for phase 0s to annihilate. Okay, so the second model is when we have a dendrite and an axon. So these have different properties, and we're putting the modulation at the point where these two meet, so the nominal Soma again. The point of The trigger position is placed along some distance along the axon. So again, we have the spatial separation. But now the main difference is synaptic drive is only present in the dendrite, as you might expect. So what we're going to do in this one, the morphological parameter we're going to vary in this model is the length constant of the axon. And this stands in for the radius of the axon, diameter of the axon, how thick it is. So a wider axon will have a larger length constant. And we see that as we increase this length constant, that the amplitude of oscillations increases, and we now have the emergence of two phase zeros. So to see why this is the case, in panel C, I plotted the ratio of length constant between, so it's axon over dendrite, and also plotted the effectively the dimensionless trigger position, so the absolute trigger position in microns over the axonal length constant. And we see that it's this reduction in the effective separation that causes the phase zeros to appear. So reducing it kind of causes it to shift to the left here in panel C. And this is analogous to the effect we saw for the two dendrites. When we decreased the spatial separation there, two phase zeros were possible. And now we're also decreasing the effective spatial separation in a different way, causing two phase zeros to be possible. So the third model, we just have a single dendrite now, but we have a large soma. So we have a soma with its own capacitance and conductance that is significant. We apply the modulation at the soma, and we parameterize it by this parameter rho. So perhaps confusingly, a small soma has a large rho, and a large soma has a small rho. And in general, we find that we have a single phase zero, and that as the somatic size increases, so going from green down to blue here, the amplitude of oscillations decreases and the phase zero frequency increases. Now, the reason for this is that the soma filters, because it's an isopotential point, it filters differently to the spatially distributed dendrite. And when we have the limit of rho goes to infinity, we're effectively have a very tiny soma, and we're retrieving the too long dendrite case we had earlier. And on the other hand, when we take rho to 0, we have a large soma, and we obtain the single point neuron model before, because all the dynamics are dominated by the huge soma. So the phase zero frequency will go towards infinity. And as another effect, if we consider the soma to have a different membrane time constant, so a different ratio of its membrane capacitance to its Lie conductance than the dendrite, then we find a slower soma also has a higher phase zero. So the takeaway is that slow large somas have a higher frequency phase zero. Okay, so as an extension, we can also consider quasi-active neurons. So long as we can linearize the active currents, which, because we're spending so much of our time looking at the voltage kind of fluctuating about equilibrium, we can do. It's obviously sensible to pick an active current which has some effect on the subthreshold dynamics like IH. And largely for simplicity, but it's not unreasonable, we're going to consider that this active current to just be equally distributed about the dendrites, and we capture it by the active parameter W. An important thing to take in mind is the active current we consider is restorative, so it dampens fluctuations away from equilibrium. And we're just going to mostly focus on the timescale tau W in this model. So we can use the same spatial model as before, but now we've made so we still have a soma and a dendrite, but now we're making the dendrite quasi-active with addition of this active IH-like current. And the main thing in the dynamic response that this adds is we now get this bump in amplitude at low frequencies, and we also get this phase zero appear corresponding to the active current. And we see that each of the phase zeros is affected differently by the parameters. So the quasi-active parameter tau W, when we make the active current slower, this has a larger effect on the range of, it's a larger effect on the lower phase zero shown in C, whilst the somatic size has a larger effect on the upper phase 0 shown in D. So, so for example, you have a larger change in frequencies for the upper phase 0 by changing rho than you will by changing the relative value of tau W. However, there is some interaction between the two. So when you have a very large soma, you need a slower active current for this first phase 0 to even be possible. Whilst conversely, when you have a faster active current, your second phase 0 will be at higher frequency. So further extensions we could build from this is we can use this for any type of weak amplitude modulation, so in the voltage variance, mean, or in presynaptic firing rates. And any structure with linear voltage dynamics could be analyzed in this way, so long as you're operating the fluctuation-driven regime. And we can apply, the next effect will apply to network context, but also with delays. So the phase 0s being representing synchrony, you know, works only if there's no delay between your output and your input. But it's a place to build from. So to conclude, I've shown how the upcrossing method can be used to approximate the dynamic firing rate response in the fluctuation-driven regime. And the main thing is that filtering from additional impedance loads, such as the soma, and spatial separation between input and output will generally reduce the bandwidth and increase the lower phase 0 frequency that we often find. And this is the existence of this phase 0 and being able to change these effects is different to what we saw for the point neuron. And for quasi-active neurons, these morphological and active current effects on the dynamic response interact. So thank you for listening. If you want to see this steady state response, you can see the paper that was published earlier this year. And are there any questions about this?
Thank you. So I will try to relay questions if there are already. So Q&R, I'm going on Slack. Okay, question from Tilo. We'll start with this one. Have you looked at the network situations? Since you know the linear response function, one should be able to compute stability of fixed points and onset of oscillation via, say, a mean field theory.
Yes, so I just need to see the question so I can. So yes, this can be. Yeah, I agree. This should. I haven't looked at it myself because it was quite took quite a while to get to this situation, but it's something that I'd like to look into in the future. So I think there would be interesting effects from this, and I think yeah, I think I agree that it should. Some work would be possible and some interesting results would happen in the network situations. I just haven't got to that situation yet with this because for one thing, you want to make sure to minimize the how many simulations you have to do. So when we have like stochastic PDEs and we're looking at rare events, these things take a long time to simulate. So you want to make sure you avoid a lot more effort than is necessary in the network context. So once you have that, once you know how to avoid kind of going for too long simulations, then I agree. I would look at the network context and then verify it by simulation.
Okay. Anyone else with a further or last question? Okay. None on Slack. I just had maybe one question. You were mentioning just before that you might take into account some delays into your model. So what kind of new or different behavior do you expect in that case?
So I'd imagine if you have like a fixed time delay, it will affect, I haven't really looked into this so much, but I would expect that you would affect different frequencies in certain ways. So it would depend on like how many periods of your oscillation fit into that delay. So I think it would depend on whether the source of your input modulation was just purely from the populations or whether you had some background as well. If you still have some background, I don't expect the effects would be too large at lower frequencies, but once you get to higher frequencies, you might, is when you, the delays would impose some kind of limits and effects on this. But it's not something I've particularly looked into. I'm just kind of saying as kind of a caveat that when we consider the sync, we need to bear in mind that there are actual delays in real systems.